McGill University. Raul did his PhD at the University of Miami in Florida, working on a CFD experiment, the quiet experiment actually. Since then, he has shifted to 21 centimeter cosmology, like a lot of people do in the world today. So he did a postdoc at Arizona State and then University of Colorado Boulder. And now he's at the McGill University working on 21 centimeter, particularly the Aegis Experiment, which has got a lot of attention the past year or so. And he's going to definitively tell us whether this experiment is right or wrong.
No.
Right? So the stakes are, the bar is set very high. Anyway, so thanks for coming. Go ahead.
Okay, thank you very much, everyone. It's a pleasure to be here. Raul Monsalve, as he said. First time in College Station, and I had the pleasure of meeting a few of you already, so it's been great. Thank you for that. So I will tell you what we have and what I can about the Aegis experiment. So hopefully the talk is accessible to most of you, and I will be happy to take questions at the end. So into the 1 centimeter cosmology, what we are trying to address is the period of the universe after the CMB was released. So between that and the end of the epoch of reionization. Okay, we have measurements of all kinds of galaxies out to redshift 6 and even further than that these days. And also we have very good measurements of the CMB, but what happened in between, in particular when the first stars and galaxies and black holes were formed, that's the period where we have the largest uncertainties right now. And if we had measurements of that period, we could constrain important models, lots of models, and very interesting physics. So how are we approaching this problem? Instead of trying to measure, detect objects and characterize those objects, our approach is to instead obtain our information from the intergalactic medium. In particular, the neutral hydrogen that, in the intergalactic medium that was left after the release of the CMB, after recombination. Okay? And with the Aegis experiment, we are nominally, and until now, we have been targeting the redshift range between 6 and 30, which corresponds roughly to the period when we expect to see the largest impact of the first sources on the 21 centimeter signal from neutral hydrogen. Okay? So, and as I said, at redshift 6, approximately, is when people think the end of reionization happened. Most of the neutral hydrogen in the IgM was extinguished, and therefore that sets a limit on the range of redshift that we can access through this measurement. Okay, so here is a diagram, a cartoon of the measurement we are trying to do. We have our telescopes here on the right-hand side trying to measure a brightness temperature, T sub B. But that brightness temperature corresponds to, it encapsulates the interaction of many quantities, physical quantities in the early universe. So we are going after the 21 centimeter signal from neutral hydrogen, gas, before and during the formation of the first sources. And this gas can be characterized in terms of its kinetic temperature, T sub K in this diagram, its ionization fraction, X sub H1 here, as well as its spin temperature, T sub S. Now, the spin temperature, we will see that later, but it's essentially an emission signal which in the rest frame occurred at a frequency of 1.4 gigahertz. Okay? And on top of that, we are seeing the interaction of all those quantities, but also given the presence of a backlight, which is in most models the CMB temperature. Okay? In this cartoon, I show that as T sub R. Okay? And now this is all evolving with redshift, and therefore all these quantities are functions of redshift, including the CMB temperature. We have measurements of the CMB temperature right now, which is 2.725, but it's been decreasing since recombination. And remember that at that time it was roughly 3,000 Kelvin. Okay, so I said that all these quantities are functions of redshift, but they are also functions of space. So in general, we could measure the spatial fluctuations of these interactions, in addition to the redshift dependence. Okay, but for the purpose of this talk, we will concentrate on the sky average effect, or global effect. What happens if at any given redshift you average over the universe? Okay, what does the interaction between these quantities look like? And then monitor that over redshift. Okay, so speaking of global evolutions, let's look at how each of these quantities evolve over redshift. So I have two diagrams here. They are cartoons, again, but hopefully they help to get the points across. Here, the x-axis corresponds to redshift, or 1 plus redshift, which is decreasing to the right, okay, contrary to the normal situations. Here it's decreasing to the right, which means that time is evolving to the right. Okay, so the CMB temperature, or T sub r, is decreasing, and it has a dependence of redshift of this kind. Essentially, as redshift increases, the temperature increases, okay? 1 plus C. Now, the kinetic temperature of the gas is colder at high redshift than the CMB, T sub K. And it has a redshift dependence that looks like 1 plus C squared, okay? Now, at some point, the first black holes form and they emit X-rays. And in typical models, people expect for those X-rays to heat up the intergalactic medium. And in that scenario, we will see this temperature going up, here represented by this dashed line, eventually above the temperature of the CMB. Okay? So that happens in most models right before the epoch of reionization. And finally, here at the bottom, I have a diagram showing the evolution of the average hydrogen neutral fraction. So in the early universe, all the hydrogen in the IgM was neutral, and therefore this fraction is 1. But during the epoch of reionization, the fraction of neutral hydrogen decreased towards 0 in a way that most people expect to be gradual when you average over space. Okay, so it goes from 1 to 0. And in most models, again, that happens after the IgM has been heated up above the temperature of the CMB. Okay, so here we have a look at some of the quantities that I described before in the picture of this measurement. Now let's look at the spin temperature of hydrogen. In a neutral hydrogen atom, when it is in its ground state, we can observe spin flip transitions that emit photons at a frequency of 1.4 gigahertz. And more specifically, what happens here is that the ground state can be in a higher energy state or lower energy state. When the spins of the proton and electron are parallel, we call this the upper ground state. It's slightly higher energy than the other state. But when the spins get reversed, which is the anti-parallel case, the energy decreases and a photon is emitted at 1.4 gigahertz, or a wavelength of 21 centimeters. Okay, so this is the 21 centimeter spectral line emission. Now, we can characterize that radiation in terms of a spin temperature, which here it's called T sub S. That temperature represents the relative abundance of particles in the upper ground state versus lower ground state. Okay, now in the early universe, during cosmic dawn, the spin temperature depended on the background radiation temperature, the kinetic temperature of the gas, as well as on the background of Lyman alpha radiation. Okay? So the dependence is complicated, and there are some coupling factors here also. The summary is that the spin temperature fluctuates between these different temperatures that are present in the early universe. Here we have a diagram showing some of some models for the spin temperature in the early universe. So I told you already about the background radiation temperature, here represented with the black line, black solid line, and the kinetic temperature of the gas, here represented by the dashed lines. And the spin temperature in the early universe fluctuates between the two, at least for a long period of time. And during cosmic dawn, during the formation of the first sources, which is here highlighted in yellow, what happens is that the first stars, they emit Lyman alpha radiation, and that radiation, as we saw here, has an effect on the spin temperature. And the spin temperature here is represented by the solid line in between the two other lines. So the spin temperature starts coupled to the CMB temperature, and because of this Lyman alpha background, there is a coupling of the spin temperature to the kinetic temperature of the gas, which is lower. So we expect to see an absorption feature that starts during the formation of the first stars due to the Lyman alpha radiation that they emit. Okay, that starts the absorption feature that we expect in the spectrum. Now, as I told you, at some point after the first stars form, the first black holes form, and they heat up the IGM. Okay, and that we see that phenomenon happening here, the IGM heating phase. Okay, what is not represented here is the epoch of reionization part. We will see that soon. Okay, so let's go back to the brightness temperature, which is what we actually try to measure. These are all physical temperatures. Temperatures that represent physics in the early universe, but this is not what we go after with our instruments. What we are trying to measure is a brightness temperature that encapsulates the physics, and it's given by this expression. There are a few factors here. One factor is the relationship between the spin temperature and the background radiation temperature here. Then another factor is the fraction of neutral hydrogen. So in the very early universe, at least for our purposes, redshifts, I don't know, higher than 20, this fraction is 1. So this brightness temperature is dominated by the ratio between the spin temperature and the background radiation temperature. The other factors are just a redshift dependence and a normalization constant. Okay, but at lower redshift, the ionization fraction decreases, and then the brightness temperature is more dominated by the fraction of neutral hydrogen. Okay, and we see that this is in the millikelvin range, so it's a small signal compared to the foreground, the intensity of the foregrounds that we also have to observe along with the cosmological signal. Okay, one final ingredient here is the redshift relationship with frequency. Remember that the spin temperature is emitted at 1.4. The emission, 21 centimeter emission line occurs at 1.4 gigahertz, but that is in the rest frame. Due to redshift, we expect to observe that radiation at lower frequencies, okay? So, following this expression. So, if we wanted to observe, for reference, at redshift 28, we will need to measure this line at 50 megahertz. And if we wanted to measure this emission line at redshift 6, we will need to measure at 200 megahertz. So, all of a sudden, to observe the period of cosmic dawn and the epoch of reionization in this redshift range, we need to do our measurement in the frequency range roughly from 50 to 200 megahertz. Okay, so for reference, the FM radio band is around 100 megahertz. So it occurs in the middle of this interesting range from the cosmology perspective. Okay, so here's a standard prediction for the brightness temperature of the global 21 centimeter signal. So it encapsulates what we have said before. Frequency is at the bottom on the x-axis, and redshift is at the top. There is an equivalence between the two, as we saw. And so the cosmic dawn period, during the formation of the first stars and galaxies, that in most models, that falls in the frequency range 50 to 100 megahertz. And above 100 megahertz, which means redshift lower than 13 or so, that's when, in most models, reionization happens, or it becomes the dominant phenomenon. Okay, so during cosmic dawn, we expect to see this absorption feature as we saw before due to Lyman alpha coupling and then X-ray heating, and then the 21 centimeter signal is extinguished during the epoch of reionization. And because of that, the brightness temperature decreases towards zero. And the y-axis shows the brightness temperature in units of millikelvin, and we can see how it's in the millikelvin range. And in standard models, in particular the absorption trough, it never goes below 200, minus 200 millikelvin. That's the lowest that it can get in standard models, given the standard models for the temperature of the IGM kinetic temperature. Okay. So if we measure this signal, we can learn about the first sources, the first stars and black holes, etc. So here are diagrams showing how the global signal could vary for different assumptions in the Lyman alpha coupling as well as the X-ray heating. So if you have more Lyman alpha coupling, the decrease of the brightness temperature will happen earlier, and that will produce a wider absorption trough that most likely will be deeper also, okay? If the coupling is more inefficient, which would be the red case here, the signal is not as deep, and the peak occurs later and is narrower, okay? Now, something similar but opposite occurs for the X-rays. If the X-rays are more efficient, that would be the blue case, the absorption trough would be smaller, it will happen earlier, and the width would be smaller. But if the X-rays are more inefficient, the signal will go deeper, the absorption trough will be wider, and the center will happen later, okay? So in some scenarios, some of these scenarios are easier to distinguish from the foregrounds than others, okay? And we will get to that. But by measuring this signal and characterizing it, we can learn about the first sources, especially on large scales in this sky average measurement. Okay, we will start talking about Aegis next, but before doing that, let me introduce you a few other global 21 centimeter experiments. We are not the only experiment trying to go after this signal. A few of them are here. One of them is called Prism. This is a collaboration between McGill University and South Africa. Actually, my colleagues right now, these days are traveling to, this is located on an island, 2,000 kilometers south of South Africa, so between South Africa and Antarctica. This is a very remote location, and we need to go to these locations to get away from artificial radio transmissions. It's similar to Aegis otherwise, but the location is different, and the team is different, and they are working on this very hard. So the other experiment is called Saras. This is another strong competitor of Aegis these days. It's from India, and they have been measuring in India until now, but I think that these days they have plans to go also to Australia. It's a significantly different experiment, different team, and they have put some interesting constraints on the signal. But they haven't had the performance until now to verify the measurement that we reported last year. Another experiment is called LIDA from the US. It's located in the Owens Valley Observatory in California. And another US experiment is called the CTP. These days it's located in West Virginia at the GBT. Okay, it's led by Richard Bradley from NRAO. Okay, so but here we'll focus on the Aegis experiment. Aegis stands for Experiment to Detect the Global EOR Signature, and it's a very small team led by Professor Judd Bowman from Arizona State University, with significant participation from Haystack Observatory through Dr. Alan Rogers. He's a radio expert, and the performance that we have reached these days, it's been to a large extent due to his input and experience. Okay, so Aegis is located in Western Australia at the Murchison Radio Astronomy Observatory. This is a radio quiet site. It's also the place where other low-frequency experiments are located or will be located. One of them is called ASCAP. It's an array targeting radio transients and other galactic science. The MWA is a low-frequency array trying to go for the signal from the epoch of reionization. And in the future, they hope to host the SKA low, which is half of the SKA radio array. The other half will be located in South Africa. Okay, it's a very interesting place to deploy instruments. Lots of animals going on, but in general, they are not source of problems. Most of the problems are caused by humans. So it's an interesting place, and remote, and in the summers it gets really hot. Okay, so here I'm showing the signal that we are going after again, but now I have added some information. We want to measure the range between when the first stars form and the end of the epoch of reionization. That corresponds to the frequency range between 50 and 200 megahertz. But due to engineering restrictions, we haven't been able to design an instrument that measures efficiently this whole range. Okay, and that's why we have divided the range into sub-ranges, and we have designed instruments that target each of those ranges specifically. That's easier than trying to measure the whole range simultaneously with a single instrument. So one of the instruments is called Aegis Low Band. Actually, we have two instruments that have measured in this frequency range between 150 and 100 megahertz. The other instrument that we deployed in 2015 is called Aegis High Band, measuring between 90 and 190 megahertz, targeting mainly the feature from the epoch of reionization. And more recently, we deployed Aegis Midband, which overlaps with the other two, and also should be able to measure the absorption feature that we reported last year from low band data. Okay, so I will tell you about these experiments in a few minutes. All these experiments share the same design. They are single antenna instruments. Also drift scan instruments. That means that the antenna is fixed, the antenna beam points to the zenith, and we just wait for the sky to rotate above us, okay? And we save data 24/7. One dipole antenna, the instrument is a total power spectral radiometer. That means that until now we haven't focused on trying to measure polarization, we just measure total power, okay? The antenna has a wide beam, almost or more than 100-degree full width half maximum. It's elliptical in azimuth, as you can see here, but it has sensitivity to most of the visible sky except to the horizon, which is good. We don't want for the instrument to have high gain toward the horizon because that's where most of the RFI is coming from, the artificial radio signals are coming from. So we have low gain toward the horizon and high gain toward the zenith. The signal coming from the antenna is taken to a front-end receiver that has low noise amplification stages as well as calibration electronics. This is an absolute calibration problem from the instrument perspective. So we have in our front-end receiver calibration electronics for that purpose. Then the signal is taken to a backend stage that has more amplification, digitization, and then after digitizing the signal in time, we compute the Fourier transform of that to get a spectrum, essentially. And spectra every 30 seconds or so. We get spectra from the sky as well as from the calibrators that we have inside the receiver, which we need in our calibration approach. Here are pictures of one of the low band antennas and of one of our receivers. So this is a wide band antenna measuring between 50 and 100 megahertz. The edge-to-edge length of the dipole, which is horizontal dipole mounted at a height above a ground plane, a metal ground plane. The edge-to-edge size is 2 meters. The height of the dipole is 1 meter above the ground plane. And we have two of these instruments. We used those two for the report of last year. And the electronics, they are operated at 25 degrees Celsius using active temperature control. The the control is very good, even though the temperature of the environment fluctuates widely and sometimes is very high, we can keep the electronics stable at the same temperature at which they were calibrated in the lab in Arizona. Okay, here are pictures of mainly of the ground plane of one of our systems. You can see here edge to edge. It has a 30 by 30 meter size. Okay, it has this shape. So it's all metal, welded metal meshes, and the edges look like triangles. Okay, and so we arrived to that design to minimize the effects of transitioning between metal of the metal of the ground plane and the soil beyond that, which is not metal. Okay, to minimize that electrical boundary, we arrive to this triangle shape at the edges. Okay, so the main challenges in this experiment are the fact that it is a very hard instrument calibration problem to get to the millikelvin performance that we are targeting to measure the cosmological signal. And also we have to look through very strong diffuse foregrounds of galactic and extragalactic origin compared to the 1 centimeter signal. From the point of view of calibration, what we need to know and do it can be summarized into these 4 points. We need to know and calibrate the gain and noise offset of the instrument. We need to know and calibrate away the impedance mismatch between the receiver and the antenna. We need to know and calibrate away the antenna and ground losses. And we need to know and calibrate away the frequency dependence of the antenna beam. The instrument has a frequency response that is not flat. And because of that, we need to be very careful and measure that passband very accurately to remove it from the measurement, and in order not to confuse an instrumental artifact from a feature in the spectrum from the sky. Okay, from the point of view of foregrounds, the foreground temperatures are very high. Here are 2 maps, one at 45 megahertz, the other one at 408 megahertz. You can see that on the galactic plane and at the galactic center, the temperatures are at 45 megahertz are more than 20,000 Kelvin, and even at high galactic latitudes, the temperature are still thousands of Kelvin. Remember that the cosmological signal is in millikelvin, so we are talking about many orders of magnitude difference between the signal we are going after versus the foregrounds. And even so, at 408 megahertz, the temperatures are lower, as you can see here. And we are talking in the tens to hundreds of Kelvin. So the temperature decreases with frequency, and even though the temperatures are strong, we think that we can discriminate between the foregrounds and the cosmological signal because the expected dependence of the foregrounds with frequency is smooth. Why? Because most of this radiation corresponds to galactic synchrotron radiation. We should have a very smooth spectral response, and which we hope to be able to separate from the spectral features from cosmic dawn. Okay, here is an example of how our instrument scans the sky. The instrument is located in the southern hemisphere at a latitude of -27 degrees. So that is represented here by the red dashed line. These coordinates are equatorial coordinates, so right ascension or sidereal time and declination. And in the background, in gray, you can see the galaxy, okay? The galactic plane in particular. So our instrument is a drift scan instrument, and sometimes, and the white and yellow lines, they represent the full width, half maximum of our antenna projected onto the sky. So sometimes we are measuring this low foreground region here, and other times we are like here, for instance, at 17.7 hours, we are pointing exactly to the galactic center. So we observe both strong foregrounds and weak foregrounds over 24 hours. Okay, so before getting to the report of an absorption feature last year, let's talk about some earlier constraints and other constraints that we have put on the global signal. So In 2017, we reported a high band spectrum and constraints that we obtained from that measurement. Here, we do not report a detection of anything other than foregrounds, but we still use these measurements to constrain models. Okay, this is the spectrum that we reported in 2017, between 90 and 190 megahertz. Okay, these are higher frequencies than the 78 megahertz where we identified an absorption feature. So this spectrum was obtained after 40 days of integration with our Aegis skyband instrument, and when observing low foreground regions. Okay, every day we took the 6 hours with the lowest foregrounds and integrated that. And after 40 days, we produced this spectrum, which has a noise level in the middle of the band, which is 140 megahertz of 6 millikelvin. Okay, so this frequency range corresponds to the redshift range of 14.8 and 6.5. Okay, so what we started doing was constrain models of the epoch of reionization. During the epoch of reionization, in most models there is an emission feature that decreases towards 0 in the brightness temperature. Okay, and we modeled that using a hyperbolic tangent model. This is a model that is used also in CMB analysis to estimate the duration and the center of the epoch of reionization. So we use a similar model, and those are the parameters. The reference redshift, the center, the 50% reionization redshift, as well as the duration, how smooth or how sharp this transition is. Okay, and so we fitted the foregrounds simultaneously with these models of EOR to the data. And we were able to disfavor very sharp reionization models. So in this figure, the x-axis is the reference redshift, or the 50% reionization redshift, and the y-axis is the duration of reionization. And the blue region here is what we can disfavor at 1 and 2 sigma significance. So essentially, we're saying that we disfavor very sharp reionization transitions with durations of up to a value delta redshift of 1 at a redshift of around 8.5. So it's interesting that this redshift between 7 and 9 is where Planck favors the 50% reionization these days. Okay, and this happened to be the range where we have the highest sensitivity, so we can rule out durations of up to 1, delta redshift of 1 over this redshift range. And for context here, we show other constraints. There are upper limits on the duration of reionization from SPT, the South Pole Telescope, and some other estimates using different observations put reionization somewhere here, again, having a redshift around 8 and with durations around 2 or 3. So we, as far as we know, we are the only type of measurement that can rule out fast reionization transitions. Okay, now, these models assume that the IGM was heated above the CMB before reionization. So they can be described as hot IGM reionization scenarios. But what happens if during reionization a heating of the IGM hadn't happened yet? So we also looked at models like those. And in those models, the global signal keeps decreasing toward lower redshifts, and then because there is no heating of the IGM. And at some point, the reionization occurs and the signal goes to 0. Okay? Now, physically, it's a little difficult to explain that, how you can have reionization happening and no heating at all. But at least we wanted to evaluate these extreme models. These are extreme models, and so we evaluated them, and the parameters are the same, the duration and redshift of reionization, but with no heating at all in the IGM. And in that case, to summarize, in that case, we rule out at more than 2 sigma significance all models in which the fraction of neutral hydrogen is less than 1% at redshift 6, which is reasonable. And with a CMB optical depth in the range between 0.086 and 0.038, which is the range where Planck favors the CMB optical depth these days. The best value these days is around 0.06 for tau. And so we constrain, so we disfavor models in this range that includes 0.06, in which there is no IgM heating prior to or during realization. The reason why we can constrain those models with high significance is because the global signal becomes deep in that range, and then most of them have translate into a feature in the spectrum that we can distinguish well, even when we also simultaneously fit for the foregrounds. Okay. Okay, so beyond, so until now I have told you about phenomenological models for the global signal. For instance, these models are hyperbolic tangent models for the EOR. These models for the EOR also are hyperbolic tangent models with the same two parameters. But recently we have moved toward constraining physical 21 centimeter models. And briefly I will tell you about that. Here, this is a recent paper from 2019 where we have constrained parameters that are part of models that come from semi-numerical simulations of the early universe. Okay, these are standard models. Here we are assuming that the absorption feature that we reported last year didn't happen. What if standard models are still valid? Okay, these are a set of standard models. In fact, we evaluated 6 million models here. And what are the parameters of these models? There are parameters that characterize early star formation, 2 of them, 2 parameters that characterize IgM X-ray heating, and 2 parameters that characterize the epoch of reionization. And here, on the right-hand side, I show you how the global signal changes for changes in each of these parameters. Okay? The red signal is a reference case that is the same in all panels, but the gray, white through black signals are changes after changes in one parameter at a time. Okay, so we fit these models simultaneously with parameters that capture the foreground contribution. And so we do this analysis, we evaluate these models using Aegis data, Aegis high band data, but also we do it using external observations. What observations specifically? The PDF for tau from Planck. So in 2018, Planck released their latest constraint on tau, which again favors a value of 0.06 for this parameter. So we use that PDF to constrain some of those other models. And also we use the PDFs for the average neutral fraction of hydrogen in the IgM at high redshift from measurements of high redshift quasars and galaxies. We have measurements of quasars at redshifts of 5.9 and 7 and 7.5, okay? And also we have measurements of galaxies at redshift 7. And those measurements can provide constraints on the hydrogen neutral fraction at those redshifts. And we use that to constrain this set of models. Okay? So when we use only the observations from Planck and high redshift quasars and galaxies, we obtain these constraints on the parameters of the semi-numerical simulations. So what can we constrain here? And of course, we can constrain tau. Okay? So Planck alone can provide a constraint on tau, but if we add the quasars and galaxies, we can refine that constraint, if you wish. So that's one parameter that that we can constrain relatively well with those observations. The other parameter is the virial circular velocity, the minimum virial circular velocity of star-forming halos in the early universe. So you can see that there is a well-defined peak here in the PDF of that parameter. The other parameters are not well constrained by those observations. For instance, the star formation efficiency in the early universe, as well as the X-ray parameters the parameters that characterize X-ray heating. In particular, the X-ray heating efficiency and the minimum frequency of the X-ray spectrum, okay? Which is a parameter in these models. But when we add the Aegis data to these observations and recompute these constraints, we see that now we start seeing constraints in the other parameters, in particular the X-ray heating parameters. We can disfavor significantly the low X-ray heating efficiency in the early universe, and also we favor low minimum frequency of the X-rays. In other words, the most likely type of X-rays that were hitting the IGM in this scenario would be soft X-rays rather than hard X-rays. Okay, so with edges we cannot put strong. It doesn't contribute too much to the minimum virial circular velocity or tau, but it can contribute to other parameters, in particular the X-ray parameters.
I have a couple questions here.
Sure.
So, this is a good question first to start with. This efficiency is, can you define that in words more? This X-ray efficiency that's greater than 1. So, like, what relative to what?
So, relative to a normalization done from observations at lower redshift, observation of the X-ray luminosity at redshifts up to 2 or 3. So, that is the normalization. That would be a value of 1. Okay, so here we
so it's just like just saying it's more, things are more efficient in the early universe.
well, again, the dark gray region is 1 sigma.
Okay.
So it's not that significant in that sense, but the peak actually is interesting that the peak is close to 1, and is efficiency significantly lower than that are disfavored. Yes.
My second question is that V sub T, that's effectively the temperature. That's derived from the temperature ultimately, right?
The minimum,
Is that correct?
the mass, the minimum.
The observable that you're measuring is something related to the temperature.
You are talking about VC.
Yeah, that thing right there, right?
Yes.
And then you're mapping on that onto like mass and circular velocity.
Yes, exactly, exactly. Okay, so we have been on top of reporting the detection with the Loba instrument. We have been constraining other models. Okay, we have phenomenological as well as more physically motivated models with other datasets. So now let's switch to the Loba detection of an absorption feature. This is what we reported last year. And in summary, we measure a spectrum between 50 and 100 megahertz. The nominal spectrum here was obtained after integrating 430 hours of low foreground regions. And here is a spectrum, and when we feed a foreground model alone, we obtain these residuals with an RMS of 87 millikelvin. And this structure here is significantly above the noise, so we asked ourselves, what does it take to explain this measurement to the noise level? And we found that it was necessary to incorporate into the model a flattened Gaussian, okay? And here I show the best fit flattened Gaussian. It's centered at 78 megahertz, and it has an amplitude of 500 millikelvin, which is the first thing that you notice is that a factor of 2 or more deeper than speculative models for the absorption feature during cosmic dawn. In fact, when you do that, the RMS of the spectrum is reduced to 25 millikelvin. Okay, so we measure that. This is the nominal spectrum, but we measure that with 2 instruments in different configurations. The instruments were separated 150 meters from each other, and we operated them rotated differently with respect to the sky. And also we made other changes to one of the instruments to rule out instrumental artifacts. And in all cases, we identified a consistent absorption feature. And if we assume that this spectral feature corresponds to the 21 centimeter signal from the early universe, you can map it to redshift, and the center would be at around redshift 17, and that in turn corresponds to an age of the universe around 200 million years after the Big Bang. Now, the start of the decrease of the temperature occurs roughly 180 million years after the Big Bang. So if this corresponds to the 21 centimeter signal, it would indicate that stars were forming significantly on large scales and impacting the IgM through Lyman alpha coupling by that age, 180 million years after the Big Bang. And the rising in temperature here, roughly 250 million years after the Big Bang, would correspond to the heating phase. And also, we see that the bottom of this feature is flatter than all models, actually. So that's another discrepancy between this measurement and standard models. Okay, we fitted the parameters of this flattened Gaussian simultaneously with foreground parameters. In most cases, we required 5 foreground parameters and 4 parameters for the 21 centimeter feature. Again, we are calling it that, putting ourselves in that scenario. The parameters are the amplitude, the center, the width, and a flattening parameter to account for that shape. Okay, so then we started, when we realized that this was a feature that was observed with 2 instruments, etc., we wanted to see how sensitive it was to possible calibration errors, among other things. So here is a table showing the recovered absorption amplitude after we changed several aspects of the calibration, several assumptions in the calibration. So what if we have, so these are estimated uncertainties on some of the calibration parameters. What if we calibrate our data adding quote-unquote errors to them, even larger than what we think they could be, and what would happen to the absorption feature? In other words, could the feature be explained by errors that are larger than we think? And we still recover the absorption feature with similar amplitude.
What kind of errors were those Gaussian errors that you introduced?
Yes, we tried Gaussian errors and also just specific single errors that we apply to, for instance, the reflection between the antenna and the receiver, beam corrections. What if we don't apply beam correction at all? What if our model for the antenna loss is wrong and we don't apply it at all, or apply something incorrect? So in some cases, we apply them randomly and in a Gaussian way. In other cases, it was just an on-off kind of test.
Right.
Okay. So another aspect that we tested was the stability of the signal with respect to foregrounds. Because if this signal is global, then it should be visible with the same properties no matter what foregrounds you are observing it through. Okay? So here we bin the data in galactic hour angle, that's essentially sidereal time. And so we computed 6-hour bins as well as 4-hour bins. And we have a spectrum for each of those cases, and we feed the signal along with a foreground model, and we recover as the signal with an absorption feature shown here in red, which fluctuates around 0.5 Kelvin, plus minus 30% or so. But the total sky temperature dominated by the foregrounds varies, as you can see, over 24 hours by a lot. It varies by a factor of up to 3 between strong foregrounds and weak foregrounds. So we don't see a strong correlation between the absorption feature and the foreground total intensity. If we had an error in our instrument calibration, the absorption feature would follow strongly the total intensity of the foregrounds. Okay, so this gave us more confidence to go ahead with reporting this measurement. And after all these tests and all the cases considered, these are, in summary, the best fit parameters. The amplitude, 500 millikelvin, center, width, 19 megahertz, flatness parameter has a value of 7, and here are the 3 sigma uncertainties. These uncertainties are dominated by case-to-case differences rather than statistical. The statistical errors are smaller than this, but between all the cases, the amplitude did vary, and I mean, here we are reporting the 3 sigma ranges. The parameter that we obtained with the highest precision, even after accounting for these systematic effects that we tested, is the center. We estimated to plus minus 1 megahertz. Okay, so how can we explain this deep absorption feature? If it is cosmological, then so going back to the beginning of the talk, I told you that in the early universe, the fraction of hydrogen is expected to be very close to 1. So therefore, the brightness temperature is dominated by the relationship between the spin temperature and the radio background. Okay? So there are two ways in which you can increase the depth of the absorption feature. One of them is by decreasing the spin temperature. And how could you decrease the spin temperature below standard models? You will need to decrease the kinetic temperature of the gas, okay? Because that sets a limit. And people have been suggesting ways of doing that. One of them involves interactions between baryons and dark matter in the universe, okay? So I will just tell you that. I'm not the expert, so I will not say anything beyond that, but probably people here are, some of them are experts and more familiar with this aspect. The other way in which you can get a deeper absorption feature is by saying, what if in the early universe the radio background was stronger than people expected? What if the CMB is not the only background light? If there is an excess radio background? So people have been thinking about ways to produce this excess. Some of them involve radio emission from early black holes. And some of them involve the decay of unstable particles. And I think that there are others, but this is just a summary of what people have been thinking about when trying to explain this absorption feature, if it is cosmological. Okay, so even given the skepticism about the measurement, this measurement still was recognized by Physics World magazine in December last year as one of the top 10 breakthroughs in the year in physics. So again, acknowledging that it is verification and that as independently as possible. But if it's true, it will be a significant step forward in cosmology. Okay, so we have, because of the skepticism within our group as well as in the community, we have continued doing measurements and verifications. So I will tell you about that briefly. Some of the concerns involve the modeling of the data. Some of the concerns involve possible instrumental artifacts having to do with ground plane effects and antenna effects. So we cannot address each aspect, every aspect simultaneously, but we are trying to go step by step, ruling out alternatives, okay? So in the field, for instance, what have we done? We have done tests that we can call node tests, in which if the signal is from the sky, we should see no signal when we measure something else, okay? And what is something else? What if we measure a noise source that should produce a flat spectrum? If we remove the antenna and we connect something else instead that should produce a flat spectrum, do we get a flat spectrum or do we get something with features? The other type of test is addresses more directly and possible antenna or ground plane effects. What if we change the antenna? If we use a different type of antenna or antenna of a different size? In this case, if we calibrate the system correctly after changing the antenna, if the feature is from the sky, we should see the feature in the same place, even though we have changed the antenna. Okay? So I will briefly tell you about this test. And the summary is that these tests have been passed successfully as far as we can see, which supports a spectral feature coming from the sky rather than from the instrument. So here, for instance, are two plots showing residuals after removing just a flat line from the spectrum when measuring 300 Kelvin passive noise sources at the input of the instrument, okay? This comes from the low band 1 instrument, remember that we have two, and this comes from the low band 2 instrument. So here we measure passive devices that should give 300 Kelvin across the spectrum. And when we measure them and integrate data, and then remove a flat line, we get residuals that are of order 25 millikelvin, and again, from each of the two instruments. And here, in green, I show the 78 megahertz for reference, where the absorption feature is that we reported last year. So this is a summary. We have done many tests of this kind, and the instrument itself is not producing the absorption feature as far as we can see, given all those tests. So now the question is, okay, let's connect an antenna back. What do we get if we change the antenna? So last year, after the report, after the paper, we changed one of the low-band instruments, and we removed the antenna and we installed a mid-band antenna. I told you about the mid-band range before, so here we go back to that. This antenna has the same, it's the same type of antenna. It's called a blade antenna, but it's 25 to 30% smaller than the low-band antenna. Okay, and it was placed on the same ground plane as one of the other two instruments. So, in many cases, in many scenarios, if the absorption feature is due to the antenna, if we make the antenna smaller, the absorption feature should shift to higher frequencies and should become smaller because now you are looking through different foregrounds, weaker foregrounds at higher frequencies. Okay, so changing this antenna should produce a change in the absorption feature. Okay, under the assumption that the feature is instrumental from the antenna or the ground plane even, because the two interact. And so to show you that this antenna is different from the low-band antennas, here this is the reflection coefficient of the mid-band antenna in green, the thick line here in the middle, compared to the two low-band systems in red. So here the point is that the lower this line is, the more efficient the instrument is over that frequency range. So we see that the low-band systems are efficient over this frequency range, and the mid-band system is efficient over this frequency range, but it should still have sensitivity, good sensitivity at 78 MHz. So with this antenna, we should be able to measure the absorption feature at that frequency if it's from the sky. Now, if it's not from the sky, the feature would be shifted to higher frequencies. Okay, so preliminarily, we are working toward publishing this, but this is what we get. The blue line that you see here is what we get from the mid-band system after removing a model for the foregrounds only. Okay, so the dashed line, it corresponds to 78 MHz, and we do observe an absorption feature here centered at that frequency. Now, here I'm showing you residuals. Again, this is new data after the paper from the mid-band system, and when we simultaneously fit a foreground model plus a flattened Gaussian model for this absorption feature, we obtain consistent parameters with those reported last year from the low-band instruments. So the feature didn't shift to higher frequencies, and the parameters remain the same. So this is a very important new information, new data that disfavors the instrument as the source of the feature and disfavors the antenna as the source of the feature. So again, we are working to publish this. Okay, so before I finish, let me tell you about upcoming experiments that I'm involved with to verify even more this measurement. I'm also part of Aegis 3, which is the third generation of this instrument. It was recently proposed to the NSF to observe from Oregon because we found a radio quiet site in that state. And so this instrument, on top of observing through different foregrounds and from a different place, it will have improved electronics, it will be a more portable design. So all that combined will serve as a good verification opportunity for the absorption feature. So we hope that we get funded, and if that's the case, we will be measuring next semester with this instrument. The work has already started toward that. And also I'm part of another experiment. It's called MIST, Mapper of the IGM Spin Temperature. This is funded by Chile, where I'm from. And so I'm working on this from McGill. The experiment right now is being developed there. And we plan to take this instrument to the Chilean Andes, relatively close to the ALMA site. It is in a place that we found to be radio quiet also. And also, we will try to measure from the Canadian Arctic. We are going there in July to a latitude of 80 degrees. This is to a place, to a base that belongs to McGill, the McGill Arctic Research Station. And we expect this place to be very radio quiet also. And from almost the North Pole, we will be looking through completely different foregrounds than from the Southern Hemisphere. Okay? So many environmental aspects will change completely. So we hope that this will serve as another verification opportunity. So I told you about other experiments beyond Aegis and beyond these two that I just told you. India, some experiments in South Africa, the island that I told you about, and also in the Americas. So on top of those ground-based efforts, there are a few space-based concepts to observe the signal from the far side of the moon, because the moon will shield the instrument from radio transmission from the Earth, as well as remove any possibility of ionospheric effects on the measurement, because the lower you go in frequency, the higher the ionospheric effects are on signals coming from the sky. So by going to the moon, you will be avoiding all that. Okay, so to measure the global signal, we are in the presence of a global effort. And so we hope that many instruments are in a position to verify the report from Aegis. And so to end my talk, I would say that before we continue favoring a spectral feature in the sky spectrum, and because we are constraining models and parameters of the early universe, even from using other data sets, and also because we're expecting similar performance from other experiments soon, we are witnessing the dawn of 21 centimeter cosmology. Thank you very much.
Questions for Raul?
So in your plots of the feature, it looked like there is another dip at the left, so around 65. Is that noise or is that real? Or?
Yeah, because that doesn't it's not consistent between instruments, between different cases. Yes, we interpret that as something specific to one data integration and one case, but it's not something from the sky.
Okay.
What foregrounds? This varying foreground, is that just ionospheric emission by and large, or?
The foregrounds are synchrotron radiation from our galaxy.
But how can it vary a factor of 2? Is it because you're pointing in different places, or?
Yes, yes.
Oh, I see.
So going back to this figure here. So this is the projection of our antenna full width half max at some hour, and here is a projection at some
Oh,
other
that's
hour.
right, it's a huge beam, yeah.
Yes, so sometimes we're pointing to the galactic plane and galactic center, sometimes we're pointing to a low foreground region.
Yeah.
Actually, it's my fault. So like, you said you for your result, you had like 6 foreground regions or something.
We tried several, but
This is like the 6 lowest ones.
well, it
So
was half of the sky. So 12. So we average over, sorry, pretty much this range, the left-hand side.
Actually, can you point, if you go back to the previous map, is it possible to point out where that is on that map, or is that just that?
Okay, so let's see.
It's hard for me to think that map.
Change projections.
It would be-
No, that's fine.
I think it would be it would be here.
So there's like 6 regions down there, like, where this is coming from. And it's a factor of 2 variation. That actually looks. So you're saying there's a factor of 2 from where? It's a factor of 2 from like the lowest emission regions?
No, there is a factor of. Okay, so when we beat the data every 6 or 4 hours, the variation in total sky temperature is of order 3. So from 1500 Kelvin to 4000 Kelvin. So this is 0 hours represents the galactic center. So this is even here, 4000 Kelvin. When we point to the galactic center, this is at 78 megahertz. And when we point 12 hours away, this 12 here, we get the.
Okay.
So going to the North Pole just gives you a different piece of this. You'll be looking at the North Polar Spur instead of the galactic center.
Well, so we will also be looking through varying foregrounds.
Yeah.
So we will be looking at this quiet region and this strong region here,
Right.
but different from the south, but also a dynamic range that is comparable.
Yeah. Okay. Well, thank you.
It's a very quick question. The Planck reionization model, can you remind me, is that just a single like reionization and a single redshift? Is that what you do?
They do obtain a duration for it.
Yeah.
So it's a hyperbolic tangent. It's very similar to what.
Oh, but they model it like, it's not a model of like.
Right.
Okay, it's a model. Okay.
Yes.
Would you care to say a little bit about the criticism from Richard Hills and your response to it?
Sure. Okay, so one of the criticisms is that we didn't constrain the foreground part, because when we fit the spectrum, we fit simultaneously a foreground model and a flattened Gaussian model. And the criticism part of it was, well, what do you obtain for the foreground parameters? Are those values realistic? And what happens is that we didn't constrain those parameters in the fit because we don't have foreground information with higher precision than what we can measure ourselves. So no other experiment can provide meaningful constraints to us. We need to fit everything simultaneously for the first time in this frequency range to this precision. And for that reason, we left everything unconstrained. All the parameters are unconstrained. And then, and also, what happens is that we are observing this spectrum through our instrument and through the ionosphere. So even if we think that we understand the astrophysical foregrounds, there are many other layers of other factors that alter this spectrum, and because of and we didn't want to put we couldn't put constraints on the combination of factors in the fit, and because of that, because when our fits are unconstrained, we obtain this the need for this flattened Gaussian. Now, in parallel to this effort, we are trying to understand the foregrounds themselves, and so we have published 2 or 3 papers, depending on how you want to count them, about the foregrounds. So this is from a paper characterizing the foregrounds using our Hyperman system, and this is from a paper from last year characterizing the foregrounds with low-band data. And we obtained spectral index information as well as curvature, like a higher order term beyond a spectral index that characterizes the foregrounds, okay, as a function of sidereal time, 24 hours. And so, but these foreground parameters are the best anybody has done at low frequencies. So we're simultaneously trying to learn about everything, and it's very difficult. So, so having said that, we still think that the naive way in which we model the data for the purposes of characterizing the spectral features is